Hello, everyone. My name is Weiran Shen, and I'm now a postdoc researcher at Carnegie Mellon University. Today, I'm going to talk about AI-driven mechanism design. So it's about how to incorporate AI techniques to help us design mechanisms. So I will start with why I studied this topic, and then I will introduce how we can use AI techniques to help us design the mechanisms. Since I don't have a lot of time, so I will only focus on these two different settings, and then I will summarize this. Why do I study AI-driven mechanism design? To answer this question, first we need to know why we need to study mechanism design. So mechanism design can help us get desirable outcomes even in settings where all the agents are strategic or self-interested. And the most successful application of mechanism design is auction. For example, the online ad auction industry. Here I've listed some of the major online ad auction platforms and the revenue of the last year. So you can see that this is a very large industry and it's still rapidly growing. Okay, we have good reasons to study mechanism design, but why do we need AI-driven? So standard mechanism design theory often makes very strong assumptions, and so as a result, it only works in much simplified settings. But in practice, we know that real-world applications can be quite complicated, and the standard mechanism design theory may not apply. But we know that in recent years, AI techniques have been quite successful in dealing with these complicated situations. So if we can somehow combine the insights and intuitions from the mechanism design theory and also like techniques from the AI domain, like machine learning models or some optimization algorithms, we might be able to solve some problems that we cannot solve before. So that's why I study this AI-driven mechanism design. So the AI-driven mechanism design framework contains two different models, quite simple. The first model is the agent model, which describes how the agent behave. It can be a theoretical model, like a rational agent. It can also be a like machine learning model learned from real data. And the mechanism model is a parameterized mechanism together with an optimization algorithm in order to optimize the mechanism parameter. And the mechanism model generates a mechanism, and then the agent model takes the mechanism as input and then acts accordingly. And if we combine the outputs of these two models, we get the outcome of this mechanism, and then we use the optimization algorithm to optimize the mechanism parameter according to the outcome. So I'm going to talk about two different settings where AI can help us design mechanisms. The first setting is the dynamic sponsor search auction design. We formulate this problem as a Markov decision process and then apply a reinforcement learning algorithm to solve the Markov decision process. So our framework has already been adopted by Baidu, which is a major Chinese search engine, and it was highlighted in Baidu's last year's Q1 financial report. So Baidu has different advertising platforms. This is a PC end, and this is a mobile end. So, but they both sell ads or ad slots through the GSP auction with reserve prices. So how does this mechanism work? We have a reserve price. first we remove all the bids that are below the reserve price, and then we sort the remaining bids in descending order and allocate the advertising slots accordingly. And each bidder pays the maximum of the reserve price and the next highest bid. Okay, so simple mechanism. But if we view this reserve price as the parameter of the mechanism, we can try to optimize this, optimize the revenue of this mechanism by setting a reasonable reserve price. Actually, this is exactly what the optimal auction theory does. So this theory tells us that reasonable reserve prices can indeed increase the revenue of the platform, but it makes some very strong assumptions. For example, it assumes that the bidders have simple utility functions which can be fully characterized by a single parameter called value. But in practice, our observations in Baidu show that the bidders may care about a lot of things other than his value. The bidders can have very complex preferences. They care about the number of impressions they get. They care about the number of clicks. They care about the amount of money they have spent so far. They also care about the ranking of their ad slots. And also, the bidders are not fully rational. They don't have access to all the information needed to compute a kind of equilibrium beforehand. So what they have access is just a bunch of performance statistics that indicates how well their advertising campaign is going. So the bidders tend to change their bids according to these performance indicators. So in order to capture this kind of bidder behavior, we propose the Markov bidder behavior model. Here we define the bidder behavior to be his bid distribution over a certain time period. So the bidder I's bid distribution in time step t+1 depends on his bid distribution of previous time steps and also the KPI statistics of previous time steps. So here KPI means key performance indicators, which includes all these things that the bidder can see in the platform. So yeah, here's the backend for the advertisers. So this screenshot shows something that the bidders can see. So for example, this is the account balance, and this is the daily budget, and this is the the spend curve, and you can switch to see the click curve and impression curve. And here's the list of keywords here, and this is the actual ranking of their ad slots. And here is the current bid of this bidder, and this column is the clicks of the last of the previous day, and this is the spend of the previous day. So these are all the statistics that the bidder can see from the platform. So with this kind of Markov behavior model, we can formulate the dynamic mechanism design problem as a Markov decision process. So the environment is just the set of the bidders, and the state of the environment is the joint bid distribution of the bidders, and our action is to set a reserve price for each bidder. And after we have set our reserve price, we can run the auctions to get all the KPI statistics to, and we send these statistics to the bidders, and the bidders, after receiving these statistics, they change their bids accordingly. And after that, we aggregate the new bids to form the state of the next time step. So here's the Markov bidder behavior model serves as a state transition function here. And Okay, to implement this framework, we first need to implement the agent model, which is the bidder model here. We choose to use the standard LSTM because we are dealing with time series data. We selected about 400 top keywords from Baidu. So Baidu has like millions of different keywords, and these 400 keywords contribute almost 10% of Baidu's total revenue. There are about 800 major bidders that are interested in these top keywords. We extracted about 8 months of data in order to train this RNN. We have the agent model. For the mechanism model, as I mentioned, the parameter of the mechanism is just the reserve price. And in order to optimize the reserve price, we choose to use the Monte-Carlo tree search algorithm to solve the Markov decision process. Of course, we can use some other algorithms like deep Q learning or any neural network-based algorithms. The reason that we choose this algorithm is that we want to decouple the bidder model and the price optimization. Suppose that we are going to update this bidder behavior model or replace it with something better. If we are using some kind of deep learning-based algorithm, we may need to retrain this neural network here. But with Monte-Carlo tree search algorithm, we don't need to change anything. So for the outcome, our goal is to optimize the revenue of the platform. Okay, so here's the our simulation results. So the bottom three curves are just are all static mechanisms, static pricing policies, and the top two curves are dynamic ones. They both rely on our Markov behavior model, and the Monte-Carlo tree search algorithm has the best performance. Okay, so here's some text I get from the Baidu's Q1 financial report. You can see that this Baidu's revenue has grown a lot in that quarter, and our reinforcement learning-based algorithm was highlighted for its ability to increase revenue. Of course, I believe that Baidu is not using the exact same policy we're using here because this policy is very, very aggressive. And but anyway, it has been adopted and apparently useful. Okay, so. This work is about how AI techniques can help us can help us solve mechanism design application problems. For the second setting, I'm going to talk about how we use neural network to solve some theoretical problems. So we focus on the multi-item auctions. We use neural network to guide us to find some theoretical results. For example, with the guidance of the neural network, we can provide the optimal mechanism in a multidimensional correlated setting. About 4 decades ago, Roger Myerson developed the optimal auction theory, which solved the problem of how to sell one item optimally. And since then, we have been working on how to extend that results to the multi-item case. But today we are still working on it because this problem is really difficult. Okay, since we are going to use neural networks to solve a theoretical problem, we use the standard mechanism design setting. So here we first focus on the single buyer case. Suppose that we have one buyer and m items. This buyer has an m-dimensional value vector which is drawn from a known value distribution. And our goal is to design a mechanism which contains an allocation function and a payment function. And we assume that the buyer's utility is additive and quasi-linear. Our goal is still to optimize the revenue of this auction subject to II and IC constraints. So why is this problem so difficult? It's because of these two constraints. So the II constraint stands for individual rationality. It says that under no circumstances can the buyer have a negative utility. And the IC stands for incentive compatibility. It says that reporting truthfully should always be the best strategy. So if you think about it, this is not a local property because you need to guarantee that for any buyer value, reporting anything else would not give the buyer a higher utility. So how to use neural network to solve this problem? The first intuition is to use the direct implementation. We could use a neural network that takes the buyer's value as input and then outputs the allocation and the payment at the same time. But apparently, this approach does not guarantee IC and IR. So another method is to try to use some domain knowledge, such as Meyerson's lemma, Rogers' lemma, something like that. The problem with this method is that it can be too specific. And it only works in settings where we have this kind of domain knowledge. And for other settings, this does not work anymore. So our approach is to use two different networks. So the first network is the agent model, and the second network is the mechanism network. So the mechanism network just generates a mechanism and feeds that to the buyer network. And then the buyer network, after seeing the mechanism, chooses the best action accordingly. And combining the outputs of these two networks, we get the outcome of the auction. And still, we optimize the revenue of this auction. It turns out that this kind of framework has a very nice economic interpretation called menu interpretation. So here's an example of a menu. So suppose that the seller tells the buyer, "You can. I have one apple and a banana. I have an apple and a banana for sale. You can buy an apple for $3, or a banana for $2, or both of them for only $4." And of course, you can just buy nothing and pay nothing. The advantage of using this interpretation is that the entire mechanism can be represented by only several parameters, like the amount of each item here and the price of each menu entry. So I'm not saying that every mechanism can be represented by just several parameters, but in some cases, using this kind of representation can significantly simplify the analysis. And compared to the original mechanism definition, which contains two different functions, now our mechanism network only needs to generate several parameters. So, of course, the most interesting thing here is that it gives us IC and IR for free. To guarantee IC, we just apply the revelation principle, which says every non-IC mechanism corresponds to an IC one. And in our case, the corresponding IC mechanism is extremely easy to construct. And to guarantee IR, we just add an exit menu entry, which is the same as the last menu entry here. So the buyer can always choose this menu entry in order to guarantee that his utility is at least 0. So we have both II and IC. With this kind of interpretation, we can simplify our network structure significantly. So in the end, both the both the mechanism network and the buyer network are just one-layer networks. Of course, one-layer networks doesn't look like network at all, but if we can solve this problem with just one-layer networks, we don't need to use a deep network. So the mechanism network just generates the allocation and payment for each menu item. And then the buyer network just chooses the best menu entry given the menu the menu that is generated by the mechanism network. And the loss function for our neural network is a negated revenue because we want to optimize revenue. We don't have any regularization term. We don't use any specific optimization algorithm, just the standard optimization algorithm to optimize any neural network. So here's some experiment results. First, we show that our neural network can reproduce some known results. For example, this is a two-item case where the buyer's value is uniformly distributed among this rectangle. We know that the optimal mechanism, the optimal menu contains 4 different menu items. So the first, so if the buyer's value lies in this gray area, then his best choice is to buy nothing. If in this pink area, his best choice is to buy both of the 2 items. So so here, these 4 color blocks stand for 4 menu entries. And you can see that there, I have some black lines here separating these colored areas. In fact, these colored areas are drawn according to the output of our network, but these black lines are drawn according to the theoretically optimal mechanism. So actually, they have nothing to do, but you can see that they are quite close. So the output, the numeric results of our neural network is quite accurate. And here's the unit demand case for which the optimal mechanism is also known. And also we are able to get some unknown results. For example, this is the case where the buyer's value is uniformly distributed in this triangle. So it's a correlated distribution. The optimal menu contains either 3 or 4 menu items, and this is the case where the menu are only allowed to have 3 menu items. So in some cases, we want to make the mechanism as simple as possible, so that the buyers can easily understand that. As I mentioned, that the output of our neural network is quite accurate, and guided by those numerical results, we can actually come up with the theoretical optimal mechanism. And of course, we can prove that they are indeed optimal, but the proof is rather involved. I'm not going to talk about them there. So that's the that's the single buyer case. For the multi-buyer case, this problem is much more challenging. In the multi-buyer case, the seller needs to give each buyer a menu, and each buyer's menu is actually a function of other buyers' values. So we're still working on this, but the major challenges we have are listed here. So the first challenge is the feasibility constraint. For example, if 2 buyers wants to buy, if multiple buyers want to buy the same item, we have a feasibility problem. But ideally, the menu that are all the menus that are given to all the buyers should guarantee that when these buyers choose the best menu entry, there will not be any feasibility problem. But for now, we're still working on that. The second problem is that even we're given very accurate numerical results, how to come up with the closed form solution. Well, we need to construct some closed form solutions that describe the numerical results perfectly. And the third challenge is that given a closed form solution, how can we prove that they are optimal? So of course we can use primal dual analysis, but in that case we not only need the closed form solution to the primal problem, we also need to come up with the solution of the dual problem. So that's also quite difficult. Okay, to summarize, the AI-driven mechanism design framework combines techniques from both the mechanism design theory and techniques from the AI domain, and it can help us relax some strong assumptions in mechanism design theory, and it also can help us optimize the mechanism parameters automatically to get a mechanism that has desirable performance. Okay, thank you.
This is regarding the challenges you described earlier. So I would like to know, first off, can you get a lower bound on the optimality of the output of the neural network? And secondly is, can you somehow deduce heuristics judging from the structure of the networks after you trained it, for to deduce heuristic for the more general case?
So for the first question about performance guarantees, no, I don't think we have considered that, because our initial goal is to to find the optimal mechanism, and even if we have some kind of numerical results, we're still not sure how to come up with a reasonable approximation ratio. So no, we don't know. And for the second question, so what do you mean by heuristics?
So you solve specific instances of the problem.
Yes.
And so perhaps you can generalize the solution, judging, for example, looking at the weights of the parameters of the networks, and then come up with understanding about how the heuristics manifest themselves in the network.
That's an interesting question. We haven't considered that yet. We did check the weights of the network, but we only check that because we want to ensure that the output is correct. So we didn't actually consider that.